Okay, I think we are live. So, yes, let me know if you guys can hear me properly or if you have some trouble hearing me. Um, so, meanwhile, I'll try to open up the whiteboard. Let me know if I'm audible or if I'm not. Okay, audible. Awesome. Let's just wait for the whiteboard to open, and meanwhile, uh, I'll quickly like explain what are the problems that we'll solve today. So okay, it's open. Today we'll be solving two problems again, like as we do every day. So the problems for today will be based on graphs, right? And I'll be giving you homework as well. Now, the homework problems, like I'm expecting definitely, like you'll be solving it after the class is over, or like tomorrow or someday. So just make sure that you solve the homework questions as well. They're pretty easy. One of them is good, but others are pretty easy. So just make sure that you solve them, right? So the problems we'll solve today, the first problem is you have to detect a cycle in an undirected graph. So we are given a undirected graph and we have to detect a cycle, and the corresponding problem for your homework will be detect a cycle in a directed graph. Now this will be a bit challenging. I will tell you why. Like, why is this a bit challenging? But yeah, like just try to figure out how to detect a cycle in directed graph. So we'll solve here undirected graph, which is the easy variant, but for your homework you'll be solving a directed graph. And the second problem we'll solve today is finding the number of islands. So it's we are given a matrix and we have to find the number of islands. Like there's water and land, and we have to find the number of islands, right? So let's actually start with the questions one by one. So with the first question, let's create a new whiteboard and let's wait. So okay, so what it is given, the question is you are given an undirected graph. The number of vertices is v and number of edges is e. Check whether it contains a cycle or not, right? So you have to determine if a undirected graph has cycle or not. So basically you have to return true if there is a method bool is cycle. You have to return true if it contains a cycle. You have to return false if it does not contain a cycle, right? So in this case, is there a cycle? Can anyone tell? Is there a cycle in this case? 1, 2, 3, 4, 0, 1, 2, 3, 4. Is there a cycle in this case? Can anyone tell me? Is there a cycle? Is there a cycle in this example? Yes, very good. So Udaya has said yes, and there is indeed a cycle, right? 1, 2, 3, 4, right? If you see this part, this is actually a cycle. Like you can go from 1 to 2. What is a cycle, right? What is a cycle? A cycle means that if there are if you can return to a edge, right? If you can return to a vertex, like while traveling away from a vertex, you can return to the same vertex. If you return back to the same vertex, there is a cycle. So let's say we start from 1, right? So we can go to 2, we can go to 3, we can go to 4, and then we come back to 1. So this means that there is a cycle between stuck in tutorial hill. Okay. So 1, 2, 3, 4, right? So there is a cycle 1 to 2, 2 to 3, 3 to 4, 4 to 1, right? So we see that we are returning to the same vertex after like traveling. right? After starting from a vertex, we are returning back to the same vertex. That means there is a cycle, right? Similarly, like all these nodes are within cycle, like you can start from 2 as well, and you can see that you will return to 2, 2, 3, 4, 1, 2, or 2, 1, 4, 3, 2, like this you will return back to 2. Similarly for 3, similarly for 4. So you will return, for this you will return true, that it is a cycle. For this we don't have a cycle, right? There is no cycle. Like if you start from 1, there is no way to return back to 1 without using a edge 2 times. So 1 to 2, 2 to 3, and you cannot come back to 1. So this is another important condition, that you cannot use the edge 2 times. Like if you're using a edge, you can always use the edge 2 times and return, right? 1 to 2 and again come back 2 to 1. But you cannot use the edge 2 times. In that case only it forms a cycle. So 1 to 2, 2 to 3, and you cannot return back to 1, right? So this doesn't form a cycle. So you have to do this. The expected time complexity is v plus e, or space complexity is order of v. Okay, no worries. Like just try to understand how we are solving the questions. I think that should definitely help. Like just try to understand the idea, right? How we are getting these ideas. Okay, so we have to determine if a graph has cycle, right? When does a graph have a cycle? If you think about it very carefully, any graph which is not a tree has a cycle, right? So any graph that is not a tree has cycle, right? So you can definitely use this this approach to solve. Like you can determine if the given graph is a forest of trees, or it is a single tree, or it is a graph, that is it has a cycle. Other than that, what we can do is we can go for a simple approach as well. We can just do a DFS, right? Like let's just think how we'll detect a cycle. So let's say we have something like this, right? So there is a cycle. So let's say we start our DFS from this node. So whenever we start our DFS, let's mark our node with a different color. So we have visited this node, so we'll mark it red. Now we are DFSing to this one, so we have visited this node, we are marking this red. From here we can DFS only to this node, so we are marking this red. From here we are going to this node, we are marking this red. From here we are going to this node, we are marking this red. Now from here we are again coming back to this node, and we see that we are again coming back to a node that we have already visited, right? So we are coming back to a node that we have already visited. That means there is a cycle. That is the definition. Like we have not used any edge 2 times, and we are coming back to the same node which we have already visited. So that means we have a cycle, right? So we can do it like this. Right, let's take another example to understand better. So let's say we have something like this. Something like this, right? So let's do a DFS. We'll start from this node, this is visited. Now we'll start from, we'll go to this node, this is visited. Now we'll go to this one. Again, we'll come back here, we'll go to this node because there is no subtree here. We'll come back here, so this is visited. Now we'll go to this one, let's say, so this is visited. Now we'll explore this, this is visited. Now from here we'll go here, this is visited. Now from here, if we see, if we go to this node, we are detecting a cycle then and there. Let's say we do not go to this node, instead we first go to this node. So we come here. From here, if we explore, right? From here, if we explore, we see that there is again a cycle. Like we are coming back to this one. Let's say this was not there, right? This was not there, so we haven't detected a cycle yet. So it will come back here. Now from here, it has already explored this part, so it will go to the next child node, that is this one, and it is already visited, right? It is already visited, so that's why there is a cycle here, right? There is a cycle here. So that's there. One thing that we have to be careful, while we are doing a DFS is, as this is a graph, right? As this is a graph, so definitely, let's say this is 1, this is 2. So 1 will be in the adjacency list, 2 will be in the adjacency list of 1, and 1 will be in the adjacency list of 2. So it's very possible that when you go to 2 and you come back to 1 again using the same edge, so you have to be sure that you are not using the same edge. So what you can do is, you can maintain another state, like similar to traversal to a tree, right? What do we do when we traverse to a tree? When we traverse on a tree, we do a DFS, right? Like this void DFS. If you remember, we take two arguments, right? Int s, int p. P is the parent, right? So similarly, we can also maintain a parent node here. So what we are basically generating is a DFS tree, right? So how would the DFS tree for this look like? So first this one would come here. First this node, then this node is coming, then this node, 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 and finally from here this node as well. So this is kind of what the DFS tree would look like, and we would see that there is a cycle here, right? We would detect a cycle in this part. So make sure like whenever make sure that when you are doing this, when you are writing the code for this, you should not use the same age, right? So 1 is contained in the adjacency list of 2, 2 is contained in the adjacency list of 1. So when you go from 1 to 2, then in 2 you will find 1 again in the adjacency list. So you should not go back to 1 again, because you will be using the same age again, right? So make sure to not use it. So for not using it, you can DFS similar to that. You DFS on a tree, you can use a similar DFS, right? You can use a similar DFS. So does this make sense? How can we quickly determine if a graph has a cycle or not? Is the logic clear? Maybe I'll take a small example and show you like what do I mean by not going. So let's say we have 3 nodes like this, right? 1, 2, 3. So what is in the adjacency list of 1? In the adjacency list of 1 will be 2 comma 3. In the adjacency list of 2 will be 1 comma 3. In the adjacency list of 3 will be 2 comma 1, right? So when we DFS, right? So when we DFS, we'll start off at 1. In the adjacency list of 1 we see 2 and 3. So first of all we'll visit 2. We'll visit 2, right? Now in the adjacency list of 2 we see 1 and 3, right? If we go from 1 here only, right, we are actually using the same age, right? We came from 1 to 2 using this age, and we are using the same age to go back to 1, which is not a cycle. So what we have to be sure about that, from we know that at 2 we came from 1, right? So we will ignore 1 from the adjacency list. We'll only go to 3. So we'll only come to 3 and mark 3 as visited. Now where are we coming to 3 from? We are coming to 3 from 2, right? So we will ignore 2 in the adjacency list of 3. We are going to only one place, that is 1. Now 1 is visited already, right? So we'll say that there is a cycle. There is a cycle. Okay. So let's write the code for this. Let me know if it is not clear with anyone. Okay. So first is okay. We have the adjacency list. What we need is we also need a visited, right? So vector bool visited. So we'll create a helper method here. So bool dfs, or yeah. So what we can do is, yes, bool dfs we can do. Yeah, we can do bool dfs, and we are at S. The parent node is P, and vector int adjacency list, right? Vector int adjacency list, we're passing this. So what we'll do first is we'll mark visited. So already if visited of V, right, if it is already visited, so if visited of S is already true, then we will return there is a cycle, so we'll return true. Else we'll mark visited of S to be true. Visited of S to be true. For int V belongs to adjacency list of S, right? So if V not equals to P, like if it is not the parent node in the DFS, like if we haven't come to this node from the parent from the node from if the current node that we are seeing in the adjacency list is not equal to the node from where we came to this node, right? So V not equals to P, that is, will not use the same age again. In that case, what we'll do is we'll let's maintain here bool is is cycle present, let's call it false, and let's do is cycle present or equals to DFS VS and adjacency list, right? So when we are DFSing to V, what will be the parent node? We are going to V from S, so the parent node for V will be S, right? So is cycle present or equals to, that means if one of them is true, then one of them returns true, that means there is a cycle. So that's why we are doing a OR, right? That means there is a cycle, so we want to capture the true, and finally what we'll do is return is cycle present. Okay, and yeah, return is cycle present, and finally what do we have here? We'll mark here visited equals to vector of bool of size will be v plus 1 and initially will be false, everything will be false, and will return DFS 0 minus 1 ADG, right? So that should be the code. Let's compile and run this and see if this is working. Any doubts with the approach? Anyone has any doubt with the approach? Okay, it's not working. Why is it not working? Okay, it's not detecting a cycle. So can there be self? Okay, I think there can be two edges. Adjacent, do not edges in the graph represent a edge. What is it given in the adjacency list? Uh, is it two integers that are given, like of size 2? Okay. Edges I0 and edges I1 represent an edge, right? Edges I0 and edges I1 represent an edge. That's weird. Adjacency list is given to us, right? So okay, I think there might be this will not work when this will not work when actually there is two edges between 1 2 and let's say 1 to 2 there is a edge and 2 to 1 there is a back edge, right? So in those cases it will not work. So I'm assuming that, will it be safe to assume that this will not be present? This should be present, right? So what we can do here is we can see how many times v2p is there, right? How many times v2p is there for all the edges. If for any edge there are if there is a self loop, one thing, right? Self loop can be there. The second thing that can be there will be self loop can be there, and the second thing will be a to b and b to a. There are two edges, basically this condition, right? So maybe this is where it's failing for us. So this condition will not be handled, right? So 1 to 2 and 2 to 1, there are indeed two edges, but we'll actually like ignore both of them, right? So this is something that we have to take care of. So how do we do that? Let's take care of that separately maybe. So first is for int I equals to 0, I less than v, I plus plus. For int v belongs to adjacency list of I. If v equals to I, return true. There is a self edge, right? The second thing that we'll check for is if v is happening two times, right? If v is happening two times, so for that we'll sort all of them and we'll say if sort uh, sort adjacency of I dot begin. But again, like that will increase the complexity. So maybe we can what we can do is we can maintain kind of a mapping here. So vector bool scene, right? Bool scene. It will be of size v, and initially everything will be false. If scene of v is true, then return true. Otherwise, set scene of v equals to true. So that will tackle the case of self loop as well. Let's actually try with a sample custom input maybe. Okay, 5504 first line should contain v and e, contain two spaced integers. Okay, let's see if we can have something. So 5 let's say 0 is connected to 1, 1 is connected to 2, 1 is connected to 2, 2 is connected to 3, 1 2 3 4, 3 is connected to 4. Okay, we have this. Also, it can be a disconnected graph as well. So we should try DFSing from all the it's not said that it is a complete connected graph, so it can be a disconnected one as well. So let's see for this one first. Okay, output 1, expected 1, and finally it can be a disconnected graph as well. So for int I equals to 0, I less than v, I plus plus. Disconnected means there can be multiple graphs. So if it is not visited, right? If a node is not visited, if not visited I, then we will run a DFS, right? We'll just run a DFS. DFS I minus 1 adjacency list. So let's hope that this works. Okay. Time limit exceeded. Why is time limit exceeded? What are we doing? Okay, for everything we are creating this, so that's why it is time limit exceeded. It's becoming n squared, so let's just not do that. So we'll create it one time, and again we'll clear it up here. So for int v belongs to adjacency list of I, and scene of v equals to false. We'll just clear everything up, right? So compile and run. Weird, it's not passing to. Anyone has any idea what is the case I'm missing? So what we can when do we have cycle? Firstly, if there is self loop will be covered here, like we are going through all the adjacency list. If there are two edges like a to b and b to a again, so in that case it will be covered here, I believe. It should be covered here. I'm not sure if the input is proper. It is not a directed graph, right? So let's add a log statement here and figure out how the graph is given to us. Cout I b ended. Let's figure out how the graph is given to us. Okay, so 0 to 4 is given and 4 to 0 is also given. 1 to 2 is given, 2 to 1 is given, 1 to 4 is given, 4 to 1 is given, 4 to 3 is given. So it's given in the expected format only. It's given in the expected format, so this is fine. Okay, we have covered this. We have covered this as well. The third case should be covered by this thing. So what is this doing? Is visited S is true, return true if it's already visited. Otherwise, visited S will set it to true. Now, if is cycle present is initially false, and we'll go through all the adjacency list. If V not equals to P, if V is not equals to P, right? V is not equal to P. In that case, is cycle present or equals to DFS VS adjacency list return is cycle present. So if cycle present is false, it will return false. If the entire subtree doesn't have a cycle, it will return false. Seeing this should take care of self loops. Any idea what am I missing? Not sure. What we can do here, we can, but this should work actually. I can make a small improvement here, like if not visited V, not visited V, else if V not equals to P. But anyways, it would be returned. It would become like true here only, right? It would just return true here only. Return true. Is or the correct thing, like true? I want true, right? We want true if there is a cycle. So yes, we want to capture true. That should be it. And visited S is true. This cycle is then V not equals to P, and visited vector bool V plus 1 false. Is cycle present should be false. It should be false. Int V belongs to adjacency list of S. If not visited V, is cycle present will be or equals to DFS VS adjacency list. That should be okay. And if else if it is not equal to the parent, in that case return true and return is cycle present. What if there's a cycle, return that, otherwise return okay. No, I don't think this will work. Not sure what the graph is, but there is something that is not working. So 1 2 3 4, are we missing any case? Okay, let's move to the second problem, and we'll come back to this one if we get some idea. So the second problem will be finding the number of islands. I'm pretty sure the logic here is okay. Maybe something wrong with the implementation or something. Self loop is tackled here, and if I have 1 2 2 1 like that, so that is also tackled here. That should also be tackled here, right? So right, that should be tackled. v equals to I, return true. That's the self loop. Yes. And if there are multiple graphs, in that case less than b I plus plus. If not visited I, then we'll do oh, why are we returning here? Sorry, not bool has cycle equals to false, and here we'll do the same thing, right? Okay, sorry, has cycle or equals to, we'll try to capture if there is a cycle, and we'll return has cycle. So that was a problem that we had done. Let's see if that works. Basically what I've done here is, if there are multiple graphs, right, if there are multiple graphs, in that case this will be the condition. Oh, it was that condition. Okay, now it's working. So basically the issue was that if we have a graph like this, right, if we have a graph like this, that I don't know why I returned there, but again, like, okay, so if we have a graph like this, 1 2 3, right, and we have another like this 4 5 6, and like this. So in that case what we should do is, we'll start a DFS from 1, we'll cover this part but will not get a cycle. So after that we should start a DFS from 4, right? So that's what we should do. What we were doing, we were returning from here only, we're returning false is the answer, but here we had a cycle, right? So it should have returned true, but we were not capturing that. So now we are actually doing a OR. So if it is true one time, it will remain true, so it will return the true, right? So that was a mistake that we were doing, and now this is solved. All right, let's go to the second problem. It is finding the number of islands. So the question is pretty simple. You are given a grid of size n cross m, and there are n rows and m columns consisting of zeros, that is water, 1 that is land. Find the number of island. What is the island? An island is surrounded by water and is formed by connecting adjacent lands horizontally, vertically, or diagonally in all 8 directions, right? So for example, 0 1, this is how it looks like, right? So if you see all the land, what is the direction we can connect? Horizontal, vertical, and diagonal, right? So if you just see into this grid, right, it is a single island, like 1 1, see, these are all connected in one part, so it is a single island. If we come to this grid, if you see, there are 2 islands here. The first island will be this part. Let me just show you what is the island here. So let's see if the snipping opens. Yes. Okay, we have the snip, I believe. Okay, in this case, this is how the grid looks like. If you look into this carefully, there are 2 islands, right? Again, the definition of island is the land is connected horizontally, vertically, or diagonally. So these are all lands, right? So these are all connected together. This entire thing is connected. But see, this land is not connected to any of these, right? So there are 2 islands. We'll tell that there are 2 islands. So this is the question, like we are given a grid like this. What is the number of islands? Now, how to solve this? So whenever you are given a grid based problem, right, grid based problem can be 2 things, it can be 3 things, right? It can be something simple like greedy, or you can actually do some ad hoc type, or generally grid based problems can be generally broken down, apart from the simple ones like the greedy or the ad hoc ones. It can be either DP problem or a graph based problem. So you can always treat a grid to be similar to a graph. So whenever it's like you have to find, you are given zeros, ones, or something like that, and you have to find the smallest path, or you have to find the number of islands or number of connected components or something like that, number of ones together, you generally treat it as a graph based problem. When do you treat it as a DP based problem? In a DP based problem, you'll only treat a grid problem, DP, whenever you see that from a cell, there is no way you can, if you start moving away from this cell, there is no way you can return back to the same cell, right? So you will only treat it like a DP problem when from a cell if you're moving away from that cell, there is no possibility of you to returning back to that cell. So in only those cases it will be considered as a DP problem, right? But in other cases, when it's shortest distance or when it's like connected components or something like that, it's generally treated as a graph, right? So how do you create a graph out of a grid? It's actually pretty simple. Like whatever rule is given to you, you just have to follow that, right? So in our case, what it was given, the lands are connected horizontally, vertically, or diagonally, right? So let's say we have something like this: 0 0 1 1 0 0 0 0 0 0 0 1 0 1. So if we see, like, how will we create a graph out of this? See, this one will be connected to this one, right? Because we can connect horizontally. This one will be connected to this one, and this one will not be connected to anything. So we essentially form two graphs, right? One will be like this, one will be a single node. So in this case, we'll tell what is the number of connected components. That is what is asked. What is the number of islands? Means what is the number of connected components, right? So there are two connected components. There are two of them, right? This one is one connected component. This one is the second connected component. So this is how we will create the graph. We will just follow whatever rules that we are given. Like if we are given the rule that it is connected 4 ways, right? If it is connected only in 4 ways, in that case we would not have connected these two, right? We would not have connected these two, and this would have been a separate connected component, right? Because this is diagonally, but as it is given, we can connect diagonally as well. So all these are connected together. All these will be connected together. So we will just follow whatever is given to us in the question, how to form the graph. We will just base it based on whatever is given to the question, and then we'll just solve that, right? So now we have created, we'll not actually create a graph, we will just use the matrix, but we can definitely do something around that, right? So let's actually see what we can do here. C++. Okay. So we are given the grid, right? We can have some methods here. Bool is valid. Is valid. In that case, what we'll do is, if a row and a column is valid, right? In column, if a row and a column is valid, and we are given the grid, vector, char, and grid, right? So if a row and column is valid, so if row is greater than equal to 0 and row is less than grid dot size, and column is greater than equal to 0 and column is less than grid dot size, grid of 0 dot size, sorry, grid of 0 dot size. Also, one more condition will come, we'll write it inside. If the next row is not water, right? If it is land only, then it is a valid cell. So if grid of row column is equals to 1, in that case will return true. Otherwise will return false. And if this is not the case, will return false again, that it is not a valid cell, right? So that will be there. Now visited will mark the visited as well. So let's keep a array for the visited. So vector bool visited, right? So we'll initialize this visited later on. Visited. Okay. So let's do a void DFS. We are currently at row and column. We'll just treat a node instead of a node, like instead of writing node like VS like that, we are just treating a node to be row and column, right? Row and column, and we are given the vector char grid as well. Vector char and grid, right? So instead of row and column, instead of a node, we are taking the row and column. So vector column grid. Let me just go to full screen. Okay. Now what we can do here, we can mark the visited, right? Visited row and column will be equals to true. Now we'll go to all the adjacent cells. So for int I equals to row minus 1, I less than equal to row plus 1, I plus plus. For int j equals to column minus 1, j less than equal to column plus 1, j plus plus. If I equals to row and j equals to column, that we are visiting the continue, we are actually looking into the same cell. Otherwise it's a valid cell, so we'll check if is valid I comma j comma grid. If it is valid, what we'll do, will dfs to I comma j. Also here one more condition will be there, is equals to 1, and then let's keep the visited on the top, right? And not visited row column, it is not visited, right? So dfs ij grid, we'll do it like this. Okay, now we are done with the dfs part. So first thing that we'll do is we'll create the visited array. So grid dot size int m equals to grid 0 dot size, and visited equals to vector int of size n, and inside that will be vector int of size m, and everything will be false initially. Let's see if we can create like this, vector int m and size false. And after that what we'll do, we'll go through all the nodes. Also we'll maintain an answer int num connected components equals to 0. For int I equals to 0, I less than n I plus plus. For int j equals to 0, j less than m j plus plus. If not visited ij, in that case what we are having a new connected component, so num connected components plus plus, and we are doing a dfs on ij with the grid. And finally return num connected